Our next example says any closed ball in a metric space is also a closed set. So suppose XD is a metric space and X is any point in my metric space capital X and R is any positive real number. Then we would like to show that closed ball centered at X of radius R is a closed set. Let's try to prove it. If we want to show our closed ball BXR is a closed set, we will have to show its complement is open. Let's try to visualize this in our Euclidean metric space R2. In Euclidean metric space R2, our closed ball looks like a circle and its interior part. So say center of this circle is X and radius is R. We want to show its complement is open. So let an element Y inside complement of my closed ball BXR. Let's try to analyze distance between X and Y. Remember, we want to find out an radius say S greater than 0 such that if I draw open ball of radius S around Y, it should totally lie inside complement of my closed ball BXR. If I analyze this distance between X and Y, I know from X till here, this distance is my radius R. And then this remaining distance, say I denote it by S. So my S I can say is equal to distance between X and Y minus radius of my closed ball, that is R. So this figure suggests me if I choose my S to be d of xy minus R, my open ball centered at Y of radius S will totally lie in my complement of closed ball BXR. Let's try to see it whether our choice of S works or not. So let Y belongs to complement of closed ball BXR. That is, Y belongs to X minus BXR. Now this BXR closed ball contains all the elements whose distance from X is less equal R. But since our Y belongs to complement of this closed ball BXR, its distance from X cannot be less equal R. Therefore, its distance has to be greater than R from X. So we have distance from X to Y is strictly greater than R. We will choose our S to be d of xy minus R. And since d of xy is strictly greater than R, I have this distance is positive. Now I want to show open ball centered at Y of radius S lies totally inside complement of my closed ball BXR. So my claim is BYS, that is open ball centered at Y of radius S, lies totally inside complement of my closed ball BXR. So let an element Z belongs to BYS. This will imply distance between Y and Z is strictly less than S. Now we will make use of triangle inequality. By triangle inequality, we have distance between X and Y is less equal distance between X and Z plus distance between Y and Z. This implies distance between X and Z is greater equal distance between XY minus distance between YZ. So I have added minus d of yz on both the side of inequality. Now look at this term d of yz. I have d of yz is strictly less than S. Therefore, minus d of yz will be strictly greater than minus S. So I have this term is strictly greater than d of xy minus S. But from here you can see d of xy minus S is equal to R. Therefore, this term is equal to R. So what you have got, d of xz is strictly greater than R. And if it is strictly greater than R, it will imply my z cannot belong to closed ball Bxr. That means it should belong to complement of my closed ball Bxr. Our Z was an arbitrary element of open ball BYS, and we managed to show that this Z belongs to complement of closed ball BXR, and this proves our claim that BYS is subset of complement of closed ball BXR, and that will mean complement of our closed ball BXR is open, and that will imply our closed ball BXR is closed set. So we have proved any closed ball in a metric space is always a closed set. Let's try to see few more examples of closed set. Say your x is R2 and your distance d is Euclidean metric, and the set given is f equal to set of all element xy in R2 such that product xy is equal to 0. We want to find out, is our set f a closed set in R2. Observe, your product x into y will be 0 if and only if either x is 0 or y is 0. Therefore, your set f represents your x and y axis in your R2 plane. Therefore, any point which does not lie on either x-axis or y-axis belongs to complement of your set f. Say, point P with coordinates x1, y1 is such point lying in f complement. It tells you that this perpendicular distance of P from x-axis is mod y1, and perpendicular distance of this point P from y-axis is mod x1. See, we want to prove f is closed. Therefore, we will have to prove f complement is open. Therefore, I want to draw an open ball of some radius around P such that that open ball totally lies in my f complement. Now this figure suggests me that I should choose my R to be minimum of mod x1 and mod y1. So my guess is, if I draw an open ball of radius r around P, that will totally lie in my f complement. That means it will not contain any point from your x-axis or your y-axis. Let's see whether our choice of r works or not. So your f complement is set of all elements xy in R2 such that x into y is not equal to 0. And we have our P with coordinate x1, y1 belongs to f complement. This means x1, y1 is not equal to 0. And we have chosen our r as minimum of mod x1 and mod y1. And we want to show open ball centered at P of radius r lies totally inside f complement. So let's take a point Q with coordinate x2, y2 inside my open ball BPR. And we would like to show this point Q belongs to F complement. That means we would like to show product x2, y2 is not equal to 0. Since Q belongs to this open ball BPR, this will imply distance between P and Q is strictly less than R. And since our distance is Euclidean distance, it will imply square root of x2 minus x1 square plus y2 minus y1 square is strictly less than R. And if you take square, it will imply x2 minus x1 square plus y2 minus y1 square is strictly less than r square. Since both x2 minus x1 square and y2 minus y1 square are greater or equal 0 and their addition is less than r square, you can say individually also these terms are less than r square. So x2 minus x1 square is less than r square and y2 minus y1 square is less than r square. Now if you take positive square root on both the side, you will have mod x2 minus x1 is less than r and mod y2 minus y1 is less than r. Remember, we want to show product x2 y2 is not equal to 0. Suppose the product x2 y2 is 0. What will that imply? Either x2 is 0 or y2 is 0. If x2 is 0, what will happen? This will imply mod of minus x1 is less than r. That means you can say mod x1 is strictly less than r. But this is contradiction. This is not possible. Why this is not possible? Because your r is minimum of mod x1 and mod y1. So your r has to be less equal mod x1. It cannot be greater than mod x1. So your x2 cannot be equal to 0. Now similarly, if y2 is equal to 0, what will you get? From here you will get mod of minus y1 is strictly less than r. And you can say this will imply mod y1 is strictly less than r. Again, this is not possible. Why it's not possible? Because for the same reason that your r is minimum of mod x1 and mod y1, it can be less equal mod x1 and mod y1, but it cannot be greater than mod x1 or mod y1. Therefore, this is not possible. So what will it imply? x2 is not equal to 0 as well as y2 is not equal to 0. That means it will imply product x2 y2 is not equal to 0. And this will imply your point Q with coordinates x2 y2 belongs to F complement. So you started with any random element Q inside your open ball BPR and you proved that element Q belongs to F complement, and it proves your claim that open ball BPR is subset of F complement. And once your claim is proved, you can say F complement is open. And this will imply your F is a closed set. Let's take one more example. It says your unit circle in R2 denoted by S1 is a closed set. That means your S1 is set of all xy in R2 such that x square plus y square is equal to 1. That means it is unit circle in R2 with Euclidean distance. We want to show this S1 is a closed set. Let's try to visualize this first. Say this is your unit circle. So it is centered at 0 of radius 1. Now if I say a point belongs to complement of this unit circle, there are two possibilities. Either your point P lies outside of this circle, or there is a possibility that your point P lies inside this circle. So consider the first case where your P lies inside the circle. Let's analyze the distance between 0 and P. We know that this total distance is radius of your unit circle, that means it is 1. So what you can say, distance between 0 and P is less than 1. Say this distance between 0 and P is equal to T. Then I have 1 minus T is greater than 0. See, we want to prove our unit circle is a closed set. That means we want to prove its complement is open. And here we have taken a point P in complement of S1. And since we want to prove its complement is open, we would like to find an radius R such that if I draw an open ball of radius R around P, it should totally lie inside complement of my unit circle S1. And it suggests me I should choose my R to be 1 minus T. We will see whether this works or not. And in the second case, where my P lies outside of this circle, then distance between 0 and P is going to be greater than 1, because radius of my circle is 1, and since P lies outside of my circle, distance between 0 and P is going to be greater than 1. So here also say T is distance between 0 and P. In this case, it suggests me I should choose my R to be T minus 1. That means we would like to show if I draw an open ball around P of radius T minus 1, it will not intersect my unit circle S1. It will totally lie inside complement of my unit circle. Let's try to see whether our choice of R works or not. So case 1, say P with coordinates x1, y1 belongs to S1 complement such that x1 square plus y1 square is strictly less than 1. That means my P lies inside the unit circle. And we have taken our T as distance between 0 and P. And we know, since we are dealing with Euclidean distance, this is equal to square root of x1 square plus y1 square. So I have my T is greater equal 0 and strictly less than 1. And here I have chosen my R to be 1 minus T. In this case, it is strictly greater than 0 because T is strictly less than 1. And we would like to show that open ball centered at P of radius R lies totally inside complement of my S1. So let a point Q with coordinate x2, y2 belong to B, P, R. This will imply distance between P and Q is strictly less than R. Remember, we want to show this Q belongs to S1 complement. That means distance of Q from 0 should not be equal to 1. It can either be less than 1 or strictly greater than 1. Let's try to see what can be distance between 0 and Q. If I make use of triangle inequality, I can say this distance is less equal distance between PQ plus distance between 0 and P. Now from here, I know distance between P and Q is strictly less than R. And distance between 0 and P I have taken is equal to T. So I have distance between P and Q plus distance between 0 and P is less than R plus T. But from here, I have R plus T is equal to 1. So overall I can say distance between 0 and Q is strictly less than 1. That means my Q does not belong to my unit circle S1, that is Q belongs to complement of S1. And since Q was an arbitrary element inside your open ball BPR and you managed to prove that it belongs to S1 complement, you have proved your claim that open ball BPR is subset of complement of S1. Now let's consider the second case where my point P lies outside of my unit circle S1. So say a point P with coordinate x1, y1 belongs to S1 complement such that x square plus y square is strictly greater than 1. Here also say T is your distance between 0 and P. Since it is Euclidean metric, you know this distance is equal to square root of x1 square plus y1 square, and it is strictly greater than 1. And here we claim that open ball BPR is subset of complement of S1 where our R is T minus 1. And since T is strictly greater than 1, we know T minus 1 is greater than 0. Let's try to prove our claim. For that, let an element Q with coordinates x2, y2 belong to open ball BPR. This will imply distance between P and Q is strictly less than R. We want to prove this point Q belongs to complement of S1. That means distance of Q from 0 is not equal to 1. Now using triangle inequality, you have distance of 0 from P is less equal distance of 0 from Q plus distance of P from Q. Now d of 0 comma P we know is equal to T, and this is less equal d of 0Q plus d of PQ. By rearranging these terms, you can say T minus distance between P and Q is less equal distance between 0 and Q. Now I have distance between P and Q is strictly less than R. Therefore, minus of d of P and Q is strictly greater than minus R. So I can say T minus R is less than T minus distance between P and Q. And T minus distance between P and Q is less equal distance between 0 and Q. Now from here I know T minus R is equal to 1. So I have 1 is strictly less than distance between 0 and Q. This implies Q belongs to complement of S1, and this will prove your claim that open ball BPR is subset of S1 complement. So in both the cases, we could find R greater than 0 such that open ball centered at P of radius R lies totally inside complement of S1. And this proves complement of S1 is open. And it will prove our closed unit ball, that is S1, is closed set.